That's recording, and do have audio. Any of you actually watch these on Canvas, then you probably noticed by now that's become a kind of a running theme for the way all of my videos start. Making sure it's recording and making sure I've got audio. Who has questions from homework? What you got? Number 13. Remember the joke about the people in prison? They would a new guy got put in jail, and he was sitting there in his cell at night, and he heard people all up and down the cell block calling out numbers, and someone would call out a number, and everyone would start laughing, and then someone else would call out another number, and everyone would start laughing, and he finally asked his cellmate, so what's going on? Why is everybody laughing? They're just calling out numbers. And his cellmate said, explained to himself, well, see, we've told the same jokes so many times, it's easier, we just numbered them, so now if we want to tell a joke, we just call out the number and everybody laughs. And the sort of new guy said, oh, okay, well, I'll try that. And he called out, 12. Dead silence. He looked at his cellmate and said, well, what's wrong? Why didn't anyone laugh? And his cellmate said, you told it wrong. Two locomotives approach each other on parallel tracks. Each has a speed of 155 kilometers per hour with respect to the ground. If they are initially 8.5 kilometers apart, how long will it be before they reach each other? Okay, so let's draw this. We got one locomotive. 13. This is 13. Am I reading the right one? Okay. One locomotive headed towards another locomotive, and yes, those are locomotives front and center. Oh, wait, no, never mind. You're caught up. They're doing 155 kilometers each. Kilometers per hour. With respect to the ground, and they are 8.5 kilometers apart. So, how would you go about solving this? Somebody snuck in on me. Now, I could have sworn I had, and I move them to a different folder. Aha, Francisco Ugalde. Right here. They're going to meet in the middle. .25 kilometers, one way to do it. How would we figure that out? Unit analysis. 155 kilometers per hour. How long will it take it to travel 4.25 kilometers. How would you do that? How would you set up the arithmetic? Because you've got kilometers per hour with hour in the bottom, and you want to know how many hours it would be. That means you're going to have to divide kilometers divided by kilometers per hour. Does everyone see why that's true? Because division is multiplication by the reciprocal. So kilometers divided by kilometers per hour, which would cancel out the kilometers, is actually the same thing as kilometers times hours per kilometer. So when you divide by something that in the denominator, the denominator of the denominator becomes the numerator. Does that make more sense? You're multiplying by the reciprocal, by kilometers times hours per kilometer. They cancel and leave hours. So what you would start with is 4.25 kilometers divide that by 155 kilometers per hour, and that would give you how many hours? Gesundheit. I need somebody with a calculator. Give me an answer, quick. 0.027 hours. How long is that? How did you get that? 60 minutes per hour equals how much? 1.64 minutes, which is equal to 1 minute and 0.64 minutes times 60 seconds per minute. What's 0.64 times 60? Say again? 38.71 seconds. So it would take 1 minute, 38.71 seconds for either train to get to the midpoint. That's a perfectly legitimate way of solving this particular problem. Just out of curiosity, this is an odd-numbered problem. What does the book say? .6 seconds? 1.6 minutes? Okay. What if the two trains weren't traveling at the same speed? What if they were traveling two different speeds and you couldn't look at it by symmetry and say, well, they're going to meet in the middle? So how long will it take either of them to get halfway across the gap? This is actually a more powerful way to solve the problem because it doesn't rely on that fortuity of symmetry. How fast is this train going relative to this train? How did you get that? You added their speeds together. Yeah. Relative to this train, this one is going 310 kilometers per hour. How did we get that? Let's start with that one. That one's going 155 kilometers per hour. That one is going minus 155 kilometers per hour. So what's the difference between them? What if they were both going in the same direction? What if one car is going 55 miles per hour and this car is going 45 miles per hour in the same direction? How fast is this one going relative to that one? You take the difference, and that's how fast it's catching up. That's how fast this one is going relative to this one. Here, you take the difference, and the difference plus 155 minus a negative 155 is 155 plus 155 is 310 kilometers per hour. Does everyone understand? Does everyone see this? We're okay, okay. Now, how long will it take this one to get to that one? Think of the relative terms as how fast is it closing the gap? This one is closing the gap at 310 kilometers per hour. So how long will it take that train to cover 8.5 kilometers at 310 kilometers per hour? Or somebody confirm that with their calculators. In fact, all of you do so. What do you get? 0.027, which we can convert from 0.027 hours to 1.64 minutes to 1 minute and 38.7 seconds. But you'll notice that this case, doing it this way, didn't matter that they were both doing the same speed. What if this one we're only doing 100 kilometers per hour? Now, how fast is this one going relative to that one? How fast is it closing the gap? Say again? Oh, well, we've got, this one is doing minus 155 kilometers per hour, minus 100 kilometers per hour. But now it's minus a positive number. So that gives us minus 255 kilometers per hour. How fast this one's going relative to this one, minus because it's going right to left. Now you just divide that same 8.5 kilometers by 255 instead of 310. You get a different answer, but it doesn't depend on any kind of symmetry that they have to be traveling the same. You can't easily look at this and go, well, wait, where are they going to meet in the middle? And do you understand how? Does everyone see the difference it makes when you start solving it in terms of relative speeds rather than absolute speeds relative to the ground? I know that's a contradiction, but I think you get the point. All right. Who else has a question? How often do you get free homework points from the teacher? Any more homework questions? Say again? I'm sorry, I was number 12. Average speed and average velocity of a complete round trip in which the outgoing 250 kilometers is covered at 95 kilometers per hour, followed by a 1-hour lunch break, and the return 250 kilometers is covered at 55 kilometers per hour. Okay, here's the picture. We start at point A at T0. We go 250 kilometers at, what was the first velocity, first speed? I did not. You're welcome. Okay. The first one's 95. And then the return is 55. Okay, so this one is at 95 kilometers per hour. Wait 1 hour, and then make the return 250 kilometers per hour, 250 kilometers at T final. This time at 55. All right, before we do anything else, turn your calculators over. No using your calculators, just your brain to do the math all by your little old self. What is the average velocity of this trip? Why? The total displacement at the end of the trip is 0. The average velocity is the total displacement divided by the time it took to get there. Okay, how long you spent or how fast you made the trip. You end up where you start, your average velocity is going to be 0. I'm going to graph this one out just to prove it to you whenever we finish the problem. Let's first start with this one. How long does it take to go 250 kilometers at 95 kilometers per hour? Time to turn your calculators back over. 250 kilometers divided by 95 kilometers per hour equals, say again, 0.38 hours times 60 minutes per hour. How many minutes? 22.8 minutes. All right, we're not going to bother with seconds. How long does it take to travel 250 kilometers at 55 kilometers per hour? 0.22 hours. $13.2 minutes. You're saying it took, we got there quicker at a slower speed? Wait, no, that's still 4.5 hours because you slowed down by less than half. Okay. Well, aren't I glad I weren't doing the arithmetic in my head? But what if I hope I'm not embarrassing you, but I want everybody to take a note of this. I've warned you about this very thing. Think about your answers. Don't just trust your calculator. It's important to ask, wait, does that make sense? You all drive. You know how long it takes to go from Tulsa to Oklahoma City. So let's try this one again. On the top, 250 divided by 95. 2.63 hours. Okay, and we'll just leave it in hours since we got a nice integer number at the beginning. What about this one? 250 divided by 55. Should be somewhere around 5. How much? 4.5. 4.54, you saying? Okay. Now that makes sense. 250, that's kind of close to 300. 90 is close to 100. 300 divided by 100 is 3. That's close to 3. Okay, that's a reasonable answer. 250 divided by 50 should be somewhere close to 5. That's a good, reasonable answer. All right, so we've got 2.63 hours, 4.54 hours, plus the 1 hour that we sat and did nothing. Well, ate lunch. That gives us 7, 11, 8.17 hours. Look at me living brave, doing arithmetic in my head. Somebody confirm it. 8.17 hours. What was the average velocity? Displacement equals x final minus x initial divided by time, which equals 0 divided by who cares equals 0 velocity. The average velocity was 0. What was the average speed? That is one of the things they ask for, right? Yeah, the average speed. How far did we travel? Not our displacement. What's our total distance? 500 kilometers. How long did it take us? 8.17 hours. Say again? 61.19 kilometers per hour. Boom. Quite a difference between our average speed and our average velocity. But again, it emphasizes the point I brought up last time, that the average velocity of the winner of the Indianapolis 500 over the course of the race is 0, no matter how fast he was driving. Now, if I could just figure out how to use that argument when I get drug into speeding court. All right. Let's do a little bit extra here and look at this graphically. On this axis, we have kilometers per hour. And on this axis, we have hours. So, for the first 2.63 hours, 1, 2, somewhere around right here, we were going 95 kilometers per hour. Then, well, let's see, that's 3 hours, this is 4 hours, so right about here, from here to here, we went 0 hours. Then, for the next 4.5 hours, you got so we go 1, 2, 3, 4.54, so we're going to be right about there. We did an average of 55 miles an hour. Now, we can see the total time is a little over 8 hours. We've already calculated that should be 8.17 hours. What happens to our velocity during this time period? Our speed or velocity, doesn't change. So our velocity is constant. Was it actually constant? No, because we sped up and slowed down, but this was the average velocity for this amount of time. So it's as though we were driving that fast, and no faster and no slower for that time period. How far did we travel? Here, we've got this many hours, so if we multiply kilometers per hour times hours, we're left with kilometers. Kilometers per hour times hours equals kilometers. That's the area of this portion of the graph. And FYI, that's what you get when you do an integral. If you integrate from here to here on this graph, you end up with the area under the curve. You multiply in kilometers per hour times hours, leaving you with kilometers, how far you traveled. Here, it's easy. Average velocity was 0 the whole time, so you traveled 0 distance. But from here to here, again, you traveled 55 kilometers per hour for, how many hours was that? 4.54 hours, which gave you this area under the curve. Again, you add both of these areas together, and you get your total 500 kilometers that you traveled and the amount of time it took to get there. I would go into this in more detail now, but I don't want to get too far ahead of the book, and I also don't want to branch off into calculus. So, does anyone have any more questions about this problem? Okay. Does everyone understand visually what we're talking about here in terms of doing the unit analysis? Okay. Any more questions from the homework? All right, well then let's go back and recap a little bit, and we'll look at section 2.4 today as well. On this graphically, we were looking at average velocity. What if we graphed our actual speed as a function of time? The graph would look more like this. Okay? This is what's talked about in section 2.3, instantaneous velocity, where you'll notice here you don't have a nice squared, cornered rectangle that you can just multiply. If you had this, if you were given a function of velocity as a function of time, then you would have no choice but to integrate it, find out how much distance you had covered. You couldn't just multiply, or you would just have to do what we did, take the average over that same amount of time, and then just multiply the average. Okay? If you look on the bottom of page 225, they do a very simplified graph of velocity as a function of time. It starts off like so, holds a steady velocity, then drops down to another steady velocity, and then finally comes to a stop here. Okay? This isn't a nice, easy rectangle to multiply to solve for. But they do draw that if you look at it this way, you've got this average velocity that you spent for the whole time. Right? We could simplify this graph, which is basically what we did here, where we had this initial time with an average velocity, gave us this much distance. A separate time with an average velocity gave us this much difference. Then we put the two together, did the calculation. What's happening right here? From here to here, velocity is not constant. From here to here, we've got a nice constant velocity. We can multiply that velocity times that amount of time to get a distance traveled. From here to here, again, we've got a nice constant velocity. But from here to here, the velocity is changing with time. Again, from here to here, it's changing with time. From here to here. Now, we could approximate this as a nice right triangle and calculate the area of the triangle, assuming that this is constant acceleration. Same here. We could estimate that as a triangle. We could estimate that as a triangle. Some of you might think that would be cheating. Why not just learn how to do an integral and then you can do the integral? Well, point of fact, oftentimes cheating like that is the only way you can solve some integrals. It's called digital or discrete mathematics. But that's a whole nother level of math that we're not even going to go close to. If you plot x as a function of time, you get position. As position changes with time, that gives you velocity as a function of time. And if velocity changes with time, that gives you acceleration as a function of time. Now, here's the good news. In this class, we're only going to deal with constant acceleration. So we're not going to deal with acceleration changing as a function of time. But in order to talk about acceleration, in order to look at it, to study it, to understand it, first thing we've got to know is, what is it? So, who can answer that question? What is acceleration? Physically, as a physicist is concerned. Let me, I got an idea. I'm going to ask the question differently. Everybody, show of hands. Everybody here knows how to drive. Everybody here drives a car. Everybody? Okay. How many accelerators are in your car? Seriously, how many? How many of you would be surprised if I told you I could think of 1, 2, 3, 4, 5 as a minimum? 5 accelerators in your car if they are used as intended. I can think of a couple more if you want to use things in ways that were not intended. Can you name, other than the long skinny one on the right, can you name any of the other accelerators? Brake is an accelerator. That's one. Steering wheel is a second one. That's another one. 2 more. Say again? Nope. That's just part of your brakes. There are 2 more that are designed specifically. You know, any of your accelerators are designed to do what? To change the velocity of your car without damaging it. Okay? That's why I say, want to use things in ways that aren't intended, then there are other accelerators too. But there's 2 more. There's one on the front and one on the back. They're called bumpers. And they are intended to change the velocity of your car without damaging it. Now, they only work at very low speeds, but they work. And that's how they're intended to work. The point is that any time you change the velocity, that's an acceleration. I know we use the word decelerate to meaning to slow down, but from a physics standpoint, deceleration is acceleration. So, since velocity is a vector, it has both a magnitude, a speed, and a direction. Anything that changes either of those quantities is a change in the velocity. So the steering wheel is absolutely an accelerator. It changes the direction of your car, that your car is moving. Now here, this is a good one. How many of you have read ahead and read the material out of the book? Have you read ahead? Have you Do any of you read the book before you come to class? You really might want to start doing that. You'd be surprised how much more you could learn if you get here with questions already in your mind. But this time it works to my advantage because that means none of you have read this little brain teaser I'm about to give you. If velocity is a change of position and acceleration is a change in velocity, if an object is at rest, does that mean its acceleration is zero? No, circle is neither a yes or a no. You could be at rest in a car. Does that mean your acceleration is zero? Why not? Well, no, now you're just talking about inertial reference frames. No, I'm talking relative to the ground. That cup is sitting there. Or let's use PHYS example. You're sitting at a red light in a car. The car is not moving relative to the earth. It's sitting right there, not moving a bit, because there's a cop parked right across the intersection, just waiting for somebody to run the red light. As long as the car is sitting at the red light at rest, as long as it has zero velocity, does that mean that its acceleration is also zero? That's a bold guess. Anyone else want to join him? Let me ask you this. If the car's acceleration is zero, how will you ever get across the intersection? You press the accelerator. The point of the brain teaser is to realize that even though the velocity is zero, that does not mean acceleration is also zero. You can have a positive, or you can have an acceleration even from rest, even from zero velocity. That's how you get from zero velocity to a higher velocity, to some faster speed, or to some slower speed. Similarly, just because a car's velocity is not zero does not mean that its acceleration is not zero. Well, that one's a confusing statement. Everybody, let's go through it a little bit at a time, see if we can figure out what I just said. Car is moving down the interstate, 100 miles an hour, 70 miles an hour, whatever the speed limit is. What's the fastest you've ever driven a car? Say again? 155? Where? Okay. Fastest I've ever driven a car was north of 170 miles an hour. And it was on I-35E, just south of Dallas. I had just bought my very first Porsche, and I wanted to see how fast it would go. And it went. So, say again? Oh, well, it may have been when I bought it, and I wouldn't make that bet when I sold it. I didn't buy it to sit in the parking lot and look at it. Me and my Porsche, 170 miles an hour down I-35 southbound, just south of Dallas. Is my acceleration Can I be moving and still have my acceleration be 0? Yes, you can. As long as your velocity is not changing. Your acceleration is 0. It doesn't matter what your velocity is. What matters is it changing? If it's changing, then you have acceleration. If it's not changing, you have 0 acceleration. So, your car is sitting at the red light at 0 velocity. You can accelerate to some positive velocity. All right? And yeah, technically speaking, when you get into 2-dimensional motion and 3-dimensional motion, even if you're going backwards, it's still considered a positive velocity. Okay? It's only a negative velocity in a 1-dimensional line. But if your position is changing, you have velocity. Or you at least have speed. And you have instantaneous velocity. You can end up where you started and have net 0 average velocity, but you're going to have some velocity as long as your position is changing. You're going to have instantaneous velocity. It may average out to 0, but that is not true of acceleration. You can, as long as velocity is not changing, then you have no acceleration. I guess the same thing would be, strictly speaking, true about position as well. If position is not changing, you have no velocity. If velocity is not changing, you have no acceleration. Next time, and I'm not going to start it now because there's too much to cover to start and try to finish it up in 7 minutes. But next time we are going to develop a set of equations that are called the kinematic equations. You're definitely going to want to be prepared to take notes. You're definitely going to want to write these equations down, and you are definitely going to want to put them on your index cards. These equations you're going to be using for the rest of this semester, and any of you who come back for Physics 2 are going to keep running into them again. And these are that important. All right, go.